Hey guys, Eli Duffy with Lab 5. Choose your own adventure. I've decided to go with momentum, a principle we haven't gone over before. The problem today is fairly simple. It is a billiard ball in motion with no net force rolling at a constant velocity towards a stationary billiard ball and analyzing the collision between them. This problem is split into three parts. The first is using Tracker to analyze the video and find the positions of ball 1 pre-collision and ball 2 post-collision. Then use those positions to determine the final velocity of ball 1 post-collision, and finally to find the change in thermal energy from the collision. An important concept we have to go over is conservation of momentum. Fairly simple. P is equal to mv, or momentum, is equal to mass times velocity. The change in momentum over time is equal to F net. If the change in momentum over time is 0, then P initial is equal to P final, thus conserving momentum. The other important concept we have to go over is one we've gone over before, which is the energy principle. In this case, we're using kinetic and thermal, so the change in energy is equal to the change in kinetic energy plus the change in thermal energy. It's good to note that while we know that kinetic energy is equal to 1/2 mv squared, we'll also be using the definition that it's equal to the momentum squared over 2m. Now we're given the diameter of the billiard ball, the weight of the billiard ball, and the video shot, which was at 3,000 frames per second. Let's look at that video now with some tracker magic done. As you can see, ball 1 moves towards ball 2 being on the right. Ball 1 moving at a constant velocity, and right here it contacts ball 2, and they move from there. Now we got some givens from this. We got the initial and final position of ball 1, and that is pre-collision, the change in time between those two. We got this initial and final position for ball 2 and the change in time there. We simply put these givens into code. As you can see along the top is the mass of the ball and the initial position and the delta t. Now we have to find momentum. Now we know that P is equal to mv. We need to find velocity as we have mass. Velocity is equal to position final minus position initial divided by delta t by the definition of velocity. Here's the equation in Python along the bottom here. You can see that we end up with the momentums. Now we have to find ball 1 final velocity, which is equal to the initial momentum minus the final momentum divided by mass. This is because there is no net force, meaning that we can apply the conservation of momentum. Here's that simple equation put into Python. Now, we ended up with a calculated ball 1 velocity of 0.98 meters per second. But looking at the ball 1 velocity analyzing the tracker video, it actually ended up being 0.79 meters per second. Now, this is for all sorts of reasons. We have friction, we have the fact that it wasn't a constant velocity, but for a more accurate reading on the thermal energy, we'll be using actual ball velocity. Now, find the change in thermal energy is using the equations we have before. It's important to note that the change in thermal energy is equal to the final kinetic energy minus the initial kinetic energy. We have the definition we spoke about before, and we're going to find that the change in thermal energy is equal to the change in energy minus the change in kinetic energy. Now it's important to know right here that we have delta E is equal to 0. There are no other energy sources in this, so we can set that equal to 0. We have Ke final. You see we have 1/2 mv squared here, and we have momentum squared over 2m here. And for Ke initial, we just use the momentum squared over 2m. And here we can find that the change in thermal energy is equal to delta E, which we know is 0, minus delta Ke. This gave us our change in thermal energy, which is 0.0152 joules. That's all. So what does this all mean? What can the change in thermal energy tell us about this collision? Well, by seeing that it's such a small change in energy, it shows that the collision was almost perfectly elastic. Perfectly elastic collision, we would have a change in energy of 0. It would mean that all of the energy goes completely to motion. Finally, a what if? What would it mean if ball 1 had a negative velocity? Well, there would either be a higher change in thermal energy, or ball 2 would have a higher velocity than ball 1 initial. It would probably be a combination of those two. Thank you guys very much for watching, and I hope you've enjoyed the series.